Hello, my name is Tim Smith, and I'm going to be talking to you about the area, circumference, arc, length, sector area, and radius measure of a circle. So, our first topic is going to be the area of a circle. Now, for our formula, we're going to have pi times the radius squared. So, for example, we have 1.5 for our radius. Now, when we plug that in, we would get pi times 1.5 squared. Right? Once we square our radius, we get 2.25 times pi. Multiply these two together, and we get 7.068. That is how you find the area of a circle. Next, we're going to talk about the circumference of a circle. So, for our formula to find the circumference would be 2 times pi times the radius. So for our example, we have our radius, which is 1.75, right? Now we plug it into our formula, we get 2 times pi times 1.75. When we multiply all of that together, we will get 10.995 for our circumference. Next topic is going to be the arc length. So our formula for finding the arc length is going to be finding the central angle, dividing that by 360, and then multiplying that by the circumference of the whole circle. So, for our example, we have our central angle, 55 degrees, and we know our circumference, which is 12.57. Alright. So once we plug in all the numbers, we will get 55 over 360 times 12.57. So we reduce 55 over 360 to get 11 over 72 times 12.57. And if we multiply these two together, we will get 1.92, which is the arc length. Next, we are going to find out our sector area. So our formula for finding our sector area is going to be area of the entire circle times arc divided by 360. So from our last formula, we're going to need to find our arc length. So I'll set it up here. Here's our angle, 125. Our area is 15.9. Our circumference is 14.137. So once we plug all that in, we're going to get 125 divided by 360 times 14.137. So once we reduce 125 divided by 360, we get 25 over 72 times 14.137. Multiply this, and we get 4.91 for our arc length. Our arc length. So all we have to do now is plug in our area and our arc length. So here we have our area, 15.9, our arc length, 4.91, divided by 360. So once we divide 4.91 divided by 360, we're going to get 15.9 times 0.014. Multiply this out, and we get 0.217. That is our sector area. Now for our final formula, we are going to find the radius measure. So our formula for finding the radius measure is going to be the degree times pi divided by 180. So here's our example. We have our degree, which is 45, and now simply we just plug it in. We go here, 45, our degree, times pi divided by 180. Once we find out pi divided by 180, which is 0.017, multiply that by 45, we will get 0.784, which is our radius measure.
On the planet of Mars, you are 100% definitely going to need to know segment length relationships regarding circles. Luckily for you, there are 3 of them. chord, secant, and secant tangent. See? 3 is the magic number. Our first theorem that we are going to be looking at is chord. This one right here. If two chords intersect inside of a circle, then that means that your equation will be part times part equals part times part. In my example, it is AS times SC is equal to DS times SB. Basically, the two parts of one segment multiplied is equal to the two parts of the other segment multiplied. Easy. We know that this equation is true because of the simple proof using angle-angle similarity. We know that these two angles are congruent because of vertical angles. And we know that these two angles are congruent because they open up the same arc. Using vertical angles and the inscribed angle theorem, we know that those two triangles are similar. Using cross multiplication and ratios set up by similar triangles, we know that our end product will be this equation, part times part equals part times part. In my example, we see that 10 times 2 is equal to 5 times 4. Basically, 20 is equal to 20. Wow! Our next theorem that we have is secant. Boom! Just a reminder that secants intersect a circle at 2 points, and they must extend outside of the circle. We see that secant BE intersects secant DE. So we know that our equation will be part times whole equals part times whole. Basically, this part times the whole thing is equal to this part times the whole thing. In my example, it is EA times EB, the whole thing, is equal to EC times ED, the whole thing. We know that this equation is true because, well, again, using angle-angle similarity. We know that these two angles are congruent because they open up the same arc. And we know that this angle is congruent to self because it's a shared angle. Using the inscribed angle theorem and the same angle, we can see that these two triangles are similar. And using our cross multiplication and our ratios, also set up by chord, we can see that our end product will equal EA times EB equal to EC times ED. Part times whole equals part times whole. My example is 4 times 4 equals 2, which is 6, is equal to 3 times 3 times 5, which is equal to 8. So we know that 4 times 6 is equal to 3 times 8, and both equal 24. Our very last theorem that we have to talk about is secant tangent. If a tangent intersects a secant outside of a circle, we know that our equation will be the tangent squared times the part times the whole of the secant. In my diagram, EA squared is equal to EC times ED. Now, we also know that that equation is true using another proof using angle-angle similarity. Again. We know that this angle is congruent to this angle because it is a shared angle between the two triangles. We know that this angle is congruent to this angle using the tangent chord theorem. Using angle-angle, we can prove that these two triangles are similar. Again, using cross multiplication and setting up ratios for similar triangles, our end product will be EA squared is equal to EC times ED. My example is 12 is equal to 8 plus 8 times 8 plus 10, 18, is equal to 12 squared. 144 is equal to 144. See? Isn't that just easy?
Hello, my name is Marco Lozzi, and I'll be going over the angle theorems of a circle. First, the inscribed angle theorem. An inscribed angle is always half the angle measure of the arc it forms. Here's an example of that. The inscribed angle right there is half the measure of the arc it forms down here. Second, the chord angle theorem. The interior angle of two intersecting chords is equal to the measure of the two arcs that the chord forms divided by 2. Here's an example of that. Either one of this or this angle equals that and that arc added together and divided by 2. Next is the second angle theorem. The exterior angle formed by two secant lines is equal to the large arc minus the smaller arc formed by the two secant lines divided by 2. Here's an example of that. So this exterior angle is equal to this large arc minus this smaller arc divided by 2. Next, the tangent radius theorem. A tangent line or segment is always perpendicular to the radius of a circle. Here's an example of that. This is the radius of a circle. Here's a tangent. It intersects at one point in the circle and is perpendicular. The next theorem is the central angle. The central angle is always equal to the measure of the arc it forms. So here's an example of that. There's a central angle, there's the arc it forms, they're the same angle measure. The last one is the circumscribed angle. The circumscribed angle is also always equal to the measure of the arc it forms. So here's an example of that. There's a circumscribed angle, there's the arc it forms, and they're equal. I also have two proofs of two of the theorems. So I have a proof for the tangent radius theorem. My proof is just the tangent of a circle is perpendicular to the radius because the tangent only intersects at one point, so it must be perpendicular to the radius. For the central angle is equal to the arc it forms because there are 360 degrees in both around the central angle and in the whole circle. Thin.
The equation of a circle is x minus h squared plus y minus k squared equals the radius squared, with hk being the center point. So, as seen here, our center is the origin, 0, 0. It's plugged in here, 0, 0. Now, notice here, you have two negative signs. And, the center of your circle may not always be both negative numbers. In that case, such as here, you would have to flip the signs. So instead of your center point being 3, negative 2, it would be negative 3, 2. Now, in order to find out if a point is on the line, you take the square root of both sides of the circle equation. So here we have 4, 0 plugged in because I'm using this point to find out if it's on the line or not, and then we have our center plugged in, and this is our radius, because our radius is 4, and 4 squared is 16. You take the square root of both sides, and it comes out to 4 equals 4. If the sides equal each other, that means the point is on the line. Now, in order to find your radius and center on a coordinate plane, for the radius, you count out from the center until you hit the circle. So in this case, 1, 2, 3, 4. So your radius is 4. In order to find the center, you count inwards from the outside line of the circle until on all 4 sides until you find the center point. So this is easy because because it's marked on the origin and all the numbers are even, but it may take a few tries if you have a circle in a different place. Hopefully this will help you on Mars when you're stuck.